Okay. Okay, so hello everyone. So I hope that everyone is doing fine. So today we have the pleasure to have Professor Julian Sonner from University of Geneva, and he's going to tell us about causal symmetry breaking and holographic quantum chaos. So over to you, Julian.
Okay, thank you. So thank you very much for the invitation. It's really an honor to speak to you. And of course, it is a shame that it has to be in this format, but let's hope we'll see each other in person again sooner rather than later. So yeah, indeed, I would like to tell you about a very general framework that is able to describe quantum chaos. In particular, of course, we're going to be interested in the context where it concerns holographic systems. And the idea is basically to describe the chaotic universal physics. So quantum chaos has universal aspects, as we like in high energy physics, the consequence of a symmetry breaking principle and the associated universal, let's say, theory of Goldstone bosons. So that's the meaning of causal symmetry breaking. And well, quantum chaos, of course, you know what that means. So okay. So mostly I'm going to report on a paper that I wrote with Alexander Altland, who is one of the experts, the world experts on quantum chaos. But I'm also going to try and talk about some recent unpublished results, which use this same framework, which are together with Alex, with Manuel Vielma, and with Pranjal Nayak, who is of course well known to many of you. So let me start with an introduction. Well, I think that for this crowd, the motivation is practically not needed, but let me say it anyway. So ADS-CFT, of course, this duality is one that relates a gravitational theory, most of the time in anti-de Sitter space, ADS, to a unitary field theory, which most of the time is a CFT. And so one of the goals one might have is that one uses the dynamics of this quantum field theory, which is, after all, an object, let's say a mathematical structure that we are much more comfortable with than full quantum gravity, to shed light on, well, in particular, the paradoxical behavior of black holes, or one could say more generally, to understand interesting aspects of quantum gravity. And the sort of way that has led me in this direction of talking about quantum chaos is actually work that I think I talked about already at various occasions in India, but this was this work in which we tried to understand how do you understand black hole formation and subsequent evaporation using ADS-CFT in terms of a controlled field theory calculation. And the idea is essentially that you set up your dual quantum field theory that dually describes the gravitational bulk in some non-equilibrium initial state. In other words, you prepare a quench type setup. And well, that is supposed to correspond in the bulk to an initial state which doesn't contain a black hole, but which then as a function of time has, let's say, a collapsing shell of matter and develops a bulk black hole with all of the features that we want, like horizons and singularities and so on. And the full future evolution of this state should allow us to diagnose the full future evolution of the black hole in the bulk. So formation, subsequent evaporation. Of course, the devil is in the details. And so it's those details that, well, many of us, I think, would like to understand. And so today I would like to essentially talk about a particular aspect of this, which is that from the field theory point of view, we are talking about some quantum thermalization problem. And many of the interesting physical effects, also from the gravitational point of view, happen at late timescales. So the strategy in general would be to study this quantum thermalization at all relevant timescales, but the ones that I would like to talk about are essentially late timescales. I will define more precisely what I mean by late. And in those timescales, a wonderful thing happens, namely that a new kind of universality arises, and which is the universality that is due to chaotic behavior of the quantum system. So, well, this is sort of the quantum ergodic regime and how we approach the quantum ergodic regime. So that's the strategy. We would like to study thermalization at all relevant timescales. And today I would like to report on timescales that have to do with quantum chaos and the approach to quantum ergodicity. So now that was the motivation, which I'm sure you all, some of you share even in your work. So I didn't really need to remind you much of that. But here is another part of the motivation, which is more specific and maybe a slightly new point of view. And so that's the idea that recently also people have started to really get puzzled about the appearance of ensembles at late times, or generally speaking, in lower dimensional holographic systems. And what could be the connection between what I just said and this idea of ensembles? Well, one way of thinking about this is actually an old conjecture in the chaos literature due to Bohigas, Giannoni, and Schmidt. And so I'm paraphrasing. They say that a classically chaotic system, one system, like, I don't know, a kicked rotor or something, or other examples, quantum mechanically actually behaves at late times like a random matrix ensemble. So that is to say that even due to the effects of quantum chaos, even an individual system actually has a sense in which it is equivalent or well approximated by an ensemble. And this equivalence arises because of chaoticity. So the idea would be that if you look at the late time behavior, so let's focus on this spectral form factor here. So if we look at the late time behavior of certain observables, then a generic chaotic system behaves as if you sampled Hamiltonians from a distribution and calculate physical quantities using that distribution. Now, this basically reflects the fact that the level spacing distribution of such chaotic systems is supposed to be well approximated by those predicted of random matrix ensembles. So this is what this figure here says. This is saying that if you take a complicated enough chaotic system and you look at its level spacing distributions, you find, so for example, this would be an example from, I think, compound nuclei. So this is from complicated nuclear physical data. This actually is well approximated by a distribution of eigenvalue spacings that follows from just assuming that the Hamiltonian is a random matrix. This is, of course, Wigner's idea, and we refer to this as the Wigner surmise. And in this case is the Gaussian orthogonal ensemble. So to repeat, the idea is that a chaotic system.
Can I ask a question?
Yes, please.
So are generic 2-point functions like, do they behave like this? Do they decay and then climb up?
Wonderful. That's actually some work that is unpublished, and I will talk about that. The answer is yes, but let me show you in detail why. But here we're talking about spectral properties for the time being. So let me continue with that. So this is a time domain manifestation. So only this sort of linear rise and then the plateau here. So only this RMT universality is a time domain manifestation of the fact that chaotic systems have some universal properties in the level spacing distribution. And the fact that this is the case is the subject of the Bohigas-Giannoni-Schmidt conjecture. Well, we'd like to basically give an argument for why this Bohigas-Giannoni-Schmidt conjecture is correct, and in particular correct for systems that are of interest to us, namely holographic field theories. Now, I would like to contrast it nevertheless. This is the second important lesson on this slide. I would like to contrast this with the recent renaissance of random matrix ensembles in the context of lower dimensional gravity. So here, what one is saying is that the entire theory, the entire gravitational theory, in other words, on all timescales, is given exactly by a random matrix ensemble. So at all timescales, two-dimensional black holes are described by random matrix ensembles. And this, of course, has recently received a big boost again, because people were able to show this in the context of JT gravity, which came out of investigations of the SYK model, and so on. But we knew about this in some sense because of earlier work on two-dimensional gravity in a different way. Okay, so again, the contrast is that a chaotic system generically will be well approximated by a random matrix ensemble, and I will tell you exactly how and why. But that's only a statement about late timescales, whereas these recent ensemble stories were about specific lower dimensional systems where this is actually an exact statement. So a fortiori, of course, they also have late time RMT behavior, but they also have it at all time scales. And so what I would like to tell you is that there is really a generic part of the story, which is the late time story. And the question is whether that helps us to answer the question whether these recent developments are just a weird feature of lower dimensions, or whether we can lift them into make them an important general lesson.
Sorry, Julian, I also have a question.
Yeah.
So the early time is, the very early time behavior is also probably pretty generic, right? I mean, if you look at the spectral form factor and you look at the right-hand side, is that correct?
Yes, it is. Yeah. Yeah.
So the question is,
but that's really given by extraordinary simple unitarity arguments, which probably you know, right? I mean, actually, you and the Kyriakos, you've thought about this quite a long time.
Yeah, indeed. So the question is, what happens at intermediate times? Is that roughly, is that the question you want to ask? Or?
No. I have at other points thought about the intermediate times, but today I really want to talk about very late times. But the intermediate times, I think I skipped that slide actually. If you wanted later on in the discussion, maybe I can unskip it, we can look at it. But indeed, as Suvra points out, there's some sort of early time universality, which here is just given by simple unitarity considerations. Then there is sort of a terra incognita in intermediate times, and then there is late time universality.
I see. Okay, thanks.
Yeah, maybe I can make a comment here. So
yes.
Yeah, so in the dip part, so there's a dip, ramp, and the plateau. So in the dip part, there is this multi-criticality in the sense that if you take a non-Gaussian matrix model with polynomial potentials like a trace of m squared plus m fourth and so on and so forth, then it sees the particular behavior of the so there's a little bit of non-universality there, but of course it's multi-criticality in the sense that there is still some more general version of universality, but it's some sort of multi-critical universality. So
right. And that could be very interesting in the context of what I'm going to say next, hopefully.
I see. Thanks.
So then the result that I would like to present is basically that, boundary theories in holographic duality exhibit late time RMT behavior. Now, the way that we establish that is we basically say that the RMT behavior, we shouldn't think of it in terms of random matrices. There is actually, in some sense, a conceptually more interesting way to think about them, which is that it is a simple consequence of a symmetry breaking pattern and an associated effective field theory that is built on the Goldstone modes of the symmetry breaking. And so I would like to explain to you what this is. We call it causal symmetry breaking. And then I would also like to give you a flavor of how you build this effective field theory of quantum chaos and how you use it to extract universal properties. And what is interesting is that as I'm emphasizing at several points, this relationship between the Goldstone effective field theory, causal symmetry breaking, and universal features is true in the correct sense, even for individual quantum systems. All right, so then let me give you already immediately an idea of what is this. So the key observable that we'd like to focus on during many parts of this talk is something like a spectral correlation function. So let us look at this R2. So we define the spectral density. We want to talk about this R2, but let's for a second think about the spectral density. So the spectral density is, basically the discontinuity of the advanced and the retarded correlation function across a cut on the real axis. Now, what you can do is you can ask in an ensemble, what is the probability of finding a level at some distance omega, given that there was an energy level at the distance e. And that's what this two-level spectral correlation function here does for us. And it is, by the way, basically it's basically the frequency domain version of the spectral form factor. This is essentially the Fourier transform of that quantity. So what does this causal symmetry breaking mean? Well, we normalize it, by the way, by the inverse square of the spectral density, which is just a standard normalization. Now, the opposite causality propagators, if they're equal, so if the advance and the retarded correlator are equal everywhere, then the spectral density obviously vanishes just by the definition here. So in fact, what you can show and what we will show is that in this case, there is even more. If it is equal to 0, then there is a symmetry which actually connects, in some sense, advanced degrees of freedom and retarded degrees of freedom. I will have to introduce to you exactly what I mean by these degrees of freedom, but let's for now just say there are some degrees of freedom which parameterize all the retarded sector of the theory and some only the, all the retarded and the advanced sector. And this turns out to be actually in our formulation, a graded symmetry group, which is a continuous graded symmetry group. So not just discrete equality, but actually there's a whole symmetry group. And then the insight is that whenever you have a non-vanishing spectral density, this symmetry here that is present if the spectral density vanishes is broken. And the breaking of this symmetry is basically the symmetry principle that we're looking for, and the Goldstone effective field theory of this will give us all of the universal features in spectral correlations, such as, for example, this R2, okay? And then the idea is, of course, not just to describe how you get this Goldstone effective field theory and how you build it and how it gives us the right predictions, but also what is its relation to a given chaotic system. Okay, so this was just the idea of where does this causal symmetry come from? Why do we call it causal symmetry? Because it links degrees of freedom that are associated to opposite causal sectors. So now, let me...
Julian?
Yeah.
So this R2 is also a function of E, right? What you call as capital E, apart from omega.
Yes, but let me fix some energy E and let's scan indifferences around that energy.
Okay. So,
but you're right, of course, yeah.
And when you say rho of E is not equal to 0, like, so you would say this, this symmetry that you're going to talk about is broken if it is not equal to 0 for even like say a band of E.
Yes.
Okay. Okay.
We will get technically to precisely what breaks it. So I was a little bit careful there, not anticipating too much, I guess, but it will be spontaneously broken, but there will also be a small explicit breaking. So this is like really pions. This is going to be like pions.
Okay, thank you.
I have a question.
Yeah.
So wasn't R2 averaged over all the E levels, like over the E's, all the levels?
No, I certainly don't want to average over all of the levels, but I have also, because I want to get into the technical details later, I have swept one thing under the rug, which is that I already showed here that there is some averaging here. Right. And we need to actually come back to what I mean by this averaging, because I also keep saying that this is true for individual systems. So these things could, if you want to do this for a theory that has some parameters, you can average over these parameters. If you have a theory that doesn't have any parameters, then you might want to average over small energy windows, but certainly not over the entire spectrum. Also, but we'll get back to this.
So if rho E is 0, is it clear that R2 is also 0? I mean, this might be naive.
If rho is everywhere 0, then the level correlation function will also be 0.
Oh, okay. And maybe could you also say what is this GLNM symmetry? Like, how do you define it?
Yes. So no, no, because I will actually build that in detail. So I'll explain that actually in technical detail. Maybe we'll postpone it to that slide.
Yeah. Thank you.
So before we go to those technical details, maybe some physical comments. So this is actually a numerical result, which of course first was popularized, made famous by Kotler and Polchinski and so on. Stanford, this long paper which studied essentially numerically the SYK spectral form factor. This here is actually from a previous paper I wrote with Manuel Vielma, the numerics we did. And what I want to say is that, okay, this takes explicitly the form that I showed schematically before. But I want to point out that the timescales that are involved, so we want to focus on basically this linear rise and then the saturation. The timescales are very interesting because the timescales are huge. The timescales are here, and one can show that this beginning here of what people like to call the ramp is a timescale that scales with e to the s. And that means that the level spacing that we're interested in is e to the minus s, which actually means that you need to control effects in this theory which are doubly exponential in the entropy. So e to the minus e to the s. And this, of course, has been, pointed out as being a big challenge. And what I want to say is that this EFT is precisely good in that regime. So it is able, first of all, to work fully non-perturbatively in e to the minus s, but it is also able to see effects that are of this size. And I want to emphasize it's able to see these effects analytically, okay? So as one example of this, so this is some numerics, but let me show you some unpublished results with Pranjal and with Manuel and also with Alex, which is also actually a reply to a previous question. So this is an analytical result which we got for 2-point functions of operators. So this sort of, the question was whether the decrease, dip, ramp, plateau also applies for correlation functions of operators. The answer is yes. There is some universal form. Here it is. This is going to be a forthcoming publication. But if you Fourier transform that into the time domain, I'm only showing you, you see here the universal timescales, which are of order already e to the s here. And this is the behavior of some operator 2-point function in the SYK model, which we obtained fully analytically, and we're able to control precisely also those features around the dip. I'm not showing you those features here. I'm only showing you the sort of ensemble RMT universal result. So this is in some sense just an advertisement, but it's nice that there was a question before. I'm not going to tell you exactly how to do this with operators. I'm going to tell you just how to do it for this kind of quantity, for the spectrum. But for the operators, I can comment how it goes maybe at the end. But so analytically, you're able to control this regime, okay? For example, in the SYK model, and we did it here in the SYK model. Okay, so that's maybe some sort of advertisement for results to be published soon. But now let's do it. So let me actually tell you how to do this, how to get this effective field theory.
Can I interrupt?
Yeah, of course, yeah.
Can we move to the previous slides? Yeah. So what is linearity in the trace of O dagger O? Sorry, constancy in this. I don't know what it is. It being plot of. I'm very sorry. What does the graph being constant signify?
Here?
Yeah.
That's basically because you normalize it by, so this is the spectral density, so we divide by this. So this factor you shouldn't think of is there. And this is basically the Fourier transform of the delta function. So S is like energy difference. I could have written omega. This is like energy difference. So if you take the delta function contribution here, you get a constant, and the value of the constant is going to be, trace O dagger minus trace O dagger. But that's just some operator trace. So this is the plateau for the operator correlation function, and it comes from the delta function contributions.
And why is it meaning? Can you signify more why this is a plateau?
Well, why don't I do this actually for this thing here? I'm going to show you how to get the one without the operator traces, which would be simpler to understand, and I can tell you then what is the plateau. Shall we do it like that?
Yeah.
So I can preview what I'm going to explain to you here. Okay, here I'm going to tell you exactly the origin of all these things. Okay, but I'd like to introduce some technical things, as you can see.
Yeah.
So let's do it. The spectral point, the point of departure is to calculate spectral determinants. Those are the quantities that are going to be the nice quantities to develop this whole formalism. So in principle,
excuse me, can I ask a quick question? Yeah. Do you consider the SYK model as a random matrix theory here?
No, the SYK model is not a random matrix theory, but it is a theory that has some random parameters in it. So if you wanted the technical way of saying the difference is a random matrix theory, you average over basically every element of an n by n matrix. And so you have n squared random parameters. So the dimension of the Hilbert space squared number of random parameters. And the SYK model has a parametrically much smaller number of random parameters. So maybe let's call the dimension of the Hilbert space L. So you have L squared random parameters, which is like e to the 2s in terms of entropy, enormous. Now, if you have the SYK model for n sides only has n to the 4th couplings, which is much smaller than e to the 2s. So it's not a random matrix. Okay.
I see.
Now, you can have, of course, systems which are even less random, and you can have systems which are not random at all. Okay, by even less randoms, for example, you might have a system where you only have one random parameter, like you apply some stray magnetic field, you just average over some component of a magnetic field. Now you really only have an order 1 number of random components. And then the extreme end is some theory that has no random parameters, where you have no handle to really randomize. Then you might want to think about energy windows. But technically speaking, the SYK model is not a random matrix theory. In fact, it's kind of parametrically far from a random matrix theory. Okay, so the fact that it behaves like an actual random matrix theory at late times is already maybe surprising, if you just look at the technicalities.
Gotcha. Thank you.
Can I ask one more question on the operator correlator ramp?
On the what?
Operator 2-point functions ramp.
Yes.
So would you still be able to see it in some larger limit, because it seems it's a difference of trace and trace
Well, you wouldn't see it anyway at infinite n, because the height of this plateau will go to 0 at infinite n at any rate. But I guess it's exactly the corrections that are interesting here. But if you wanted to see it in a large n theory, you would have to work non-perturbatively in n, for sure. It's challenging to see it.
Okay, thanks.
So good, but let's try and get a framework that is actually able to get such results, but which are non-perturbative in these parameters, and doubly non-perturbative even. So let me try it. So the point of departure is this ratio of spectral determinants. And what is the meaning of this? Well, H is the Hamiltonian of our system, and we think of Z as being some kind of energy. I'm going to look at complex analytically continued versions of this Z. And the utility of a ratio like this, you could imagine having, ratios of more than 4 determinants, 8 and so on, but let's focus on this one, because this is the one that allows me, by a simple differentiation, to get precisely the spectral 2-point function. So I take Z4, I differentiate it with respect to 2 of the energies, and then I set the energies equal in pairs. And so what is important here is that you actually have to be careful about where in the complex plane you put the z's in the denominator. So one of them has to be in the upper half plane, and the other one has to be in the lower half plane. And the reason for that is precisely that the energy, the rho, is going to be the difference of some advanced and some retarded Okay, and that's reflected here in having to put this with a plus and this with a minus. But in other words, this thing is just a gadget that you hit it with the right operator, it gives you the two-level correlation function. Let me make one innocuous remark, which is that you're only required to do this in the denominator. You're not required to do this analytic structure in the numerator, and therefore there is what's called a Weil symmetry upon exchange of Z1 and Z2. And that will be super useful. Right now, it looks like it's just some observation.
Hello?
Yeah.
So, Julian, so the L here is the dimension of the Hilbert space, or what is
L? Yes, L, yes, I understood N, sorry, yes, thank you. This is just some normalization factor that we put there.
But it is a dimension of the Hilbert space?
It is. H is like an L by L matrix.
Okay, thank you.
Thank you. I should have said that. And RE is for the real part.
What is Z1, Z2, Z3, Z4 here?
There are, like, formally speaking, 4 energies, but once you set them equal in pairs like this, then they're literally the 2 energies that come in this 2-point function here. So, you could parameterize them. E is, epsilon plus omega, and E primed is epsilon minus omega. Then we're back at this thing here. Okay.
And why do we need to plot the determinant of 2 matrices?
Yes, because, sorry, if you take the derivative of a determinant, you get something like the determinant times trace log of the operator inside the determinant. Okay. And the trace log is the resolvent, which gives you basically the spectral density, but you still have the factor of a determinant that you want to cancel. So this is like a normalization factor, if you want. Okay, so maybe that will help you, maybe not. I could also say that another way of arriving at such a generating function is to use the replica trick, which also takes care of the normalization. Here, the normalization is taken care by having an inverse determinant for each ordinary determinant.
Okay, so it's some kind of normalization of the 2-point function of the spectral form factor.
Correct. It's the right way to get the normalized 2-point function of the spectral form factor.
Okay, thank you. And why do we couldn't we had a trace rather than partition function is the trace? Is Z like the partition function?
Well, no, it's more like a generating functional for correlators of rho. That's how I want to think of it.
Okay.
So because by hitting it with derivatives, I get correlators of rho.
Okay.
So now let me do some trivial rewritings. We can trivially rewrite a determinant basically as a functional integral, or here it's a Grassmann integral. So I can just introduce some 2L Grassmann numbers eta, right? And I can write a Gaussian integral. And we know the rules of Grassmann integrals are that I get the determinant of this operator here. So, not being careful about factors of 2 pi, but more or less this is the correct formula. Now, here comes an important bit now. The inverse determinants, of course, are calculated by bosonic integrals, because if I take bosonic Gaussian integrals, I get 1 over determinants. Okay, so this whole ratio Z4, I have Grassmann degrees of freedom for each of the determinants in the numerator, and I have bosonic degrees of freedom for each of the determinants in the denominator. And so I end up with an integral over a graded vector, which has both Grassmann and bosonic components. And I have this kernel here where now Z hat is just a matrix that contains Z1, Z2, Z3, Z4, and H is essentially 4 copies of our Hamiltonian. And each of them is in their own sector, right? So we have now, we have Grassmann and bosonic sectors, but we also, I remind you, if we go further into detail, we have 1 sector for each energy here. And so one of them will be advanced and one of them will be retarded. And so now we have degrees of freedom, which are basically parameterizing the retarded determinants, and degrees of freedom which parameterize the advanced determinant. And this is what I call advanced and retarded degrees of freedom. But so far we have done a essentially trivial rewriting of a ratio of determinants. The idea is now that what we actually find is that if you look at a sufficiently chaotic system, then the actual contributions that are dominant, the dominant contribution to this integral, are actually the ones that have to be phase coherent. So they have to be paths that go forward and backward along the same sequence of scattering events. And so I will motivate this a little bit further, but let me just say the point is that precisely what that means is that the only degrees of freedom that give a dominant contribution are the ones which are actually singlets under this free index, the Hilbert space index. Remember, L parameterized all the whole basis of the Hilbert space. And so I actually have to go to the sector which is a singlet under these L indices. And the remaining part of the symmetry group is just a 2/2 symmetry, okay? And this 2/2 symmetry is precisely what we call the causal symmetry. Now, how do we understand this singlet projection here?
Sorry, Julian, can you just, maybe there's some point I'm not understanding. Why is it like GL of 2L rather than GL of L cross GL of L? Like,
rather than what?
So you have like 4 copies of the, the Hamiltonian, right?
Yeah.
So
I have two fermionic and 2 bosonic copies if you want.
Okay. And so I would think in let's say just the bosonic case, the full Hamiltonian would be, I think, H, right, in the diagram, in the block diagram.
So that would be 2L, right?
Okay, you're saying that this matrix is invariant under whole 2L transformations. Is that okay? Okay, maybe I'm not.
No, the invariance is precisely once you project it on the singlet sector. That's important.
But the action itself, you're saying, is invariant under this whole the supergroup.
No, the action is not invariant under the supergroup, actually. No, it is not, because H will break that. H will break it.
Oh, okay. So then I didn't understand. So what is the supergroup acting?
The supergroup under which the action will be invariant is this GL2/2, which is the singlet sector on Hilbert space.
Okay. And
so let me actually go on, and I think you'll see what's going on.
I just wanted to understand this particular statement which appears in the last slide, where you say there's a natural GL2L action.
Action, yes, action.
So can you just say, maybe 1 or 2 sentences about what do you mean by that sentence?
Well, that basically psi and psi tilde are 4L dimensional graded objects, and so I can think of acting psi with a GL 2L transformation into some transformed psi tilde.
Okay. Yes. Okay. I understand. Thank you.
But I'm not saying that the term in particular psi bar H psi is invariant under it. What is invariant is the singlet sector. And the point is that this singlet sector is actually the one that survives chaotic dynamics. So let's see how it works in a simple analytical example. Okay. So one way to see it is, let's step back and one particular example in which this effective field theory arises is actually random matrix theory itself. Okay, and so this is something that illustrates maybe the question that Loga had. So here, what I do is, rather than saying that the dynamics will project on singlets, I actually show that the integral over H that I do for a random matrix theory precisely projects on singlets. And why is that? Well, I'm going to integrate this now. So now I'm going to consider my spectral determinants here, and I'm going to integrate over H. That means that the only thing that can survive after the integral is contractions that contract psi, the index psi bar Hilbert space index with the Hilbert space index on psi. So if the Hilbert space index were mu, for example, that runs from 1 to, in this case, 4L, because it's 4 copies of it, then the resulting theory will be a theory that has non-trivial interaction terms in psi, but all of them will be singlets under this GL2/2 subgroup, and the resulting action will be invariant under GL2/2.
Sorry, what was V?
V can be any random matrix potential, but if you want, you can put the Gaussian potential here. But that basically defines the measure with respect to which I integrate here. Okay. And so now you have a theory which is actually invariant under these singlets, GL2/2. And GL2/2 is the causal symmetry group. So now what is important is that, however, we knew that rho, the non-zero rho, actually breaks any symmetry that there could be between advanced and retarded degrees of freedom. So in particular, this remaining singlet G2/2 symmetry has to be broken. And it has to be broken into the only thing that remains, which is the retarded and the advanced degrees of freedom separately can be rotated. Okay, GL1/1 times GL1/1. And this now gives a spontaneous breaking of that causal symmetry, and therefore a Goldstone effective action, which basically is described by this coset here. So it is GL2/2 divided by GL1/1 times GL1/1. So let me see. So now I guess I don't need to tell you that once you know the symmetry breaking pattern and you know that there's spontaneous symmetry breaking, we can basically use the full machinery of, I guess, Callan, Coleman, Vestomino, and others to build the theory of these. But before I do that, I feel like maybe we should just, would you like to discuss now one more time how we arrived there, or should I go on for now and we can maybe postpone to later? I feel like the most difficult thing to swallow in some sense is we introduce basically these auxiliary degrees of freedom. There is a natural GL2L/2L action, which, however, as Loga already pointed out, this is broken by the Hamiltonian itself. So there's a natural action which rotates these degrees of freedom, but it's broken by the Hamiltonian. The main insight is that the processes that actually give the dominant contribution at late times are precisely the ones which are singlets under this Hamiltonian. And this leaves you with a GL2/2 symmetry. And now why am I, okay, let me maybe give you one more piece of ingredients here. I'm trying to build this, of course, without referring to specific models too much, because I want to, build an effective field theory, which is somewhat agnostic to the microscopic details. But there exist microscopic ways of deriving this in certain cases. SYK is one example. I just showed you, in random matrix theory, it's super easy, but random matrix theory, it's not surprising that random matrix theory behaves like random matrix theory, right? It's a tautology. But there exist microscopic derivations of this effective field theory, for example, for the SYK model and for various other chaotic systems. However, for a general chaotic system, such a derivation does not exist. And if such a derivation existed, it would amount to a proof of this BHG conjecture, a BGH conjecture, right? I didn't tell you that I proved this. If I could show that for a generic system, what I say is true, I would have proved this conjecture, okay? But as you know, effective field theories are interesting, is especially interesting in contexts where you don't have a microscopic derivation. Like, for example, the pion effective Lagrangian. Okay, they're powerful exactly in those contexts. So I didn't want to bother you with too many examples where we can microscopically derive it. But let me just reassure you that, for example, in the SYK model, it can be established actually with all the H's crossed and all the I's dotted. Okay. So is that point of view more or less clear?
Julian, if I may just ask one question, this coset that you're writing in the previous slide, like what is the bosonic and the like order the
it's hyperbolic 2 space times a 2 sphere, and the bosonic part is hyperbolic 2 space, and the fermionic part is the sphere, and both of them will actually play important and nice roles.
Okay, so you have a full Goldstone multiplet, so like super multiplet, if I may say so, in this sense. Okay. So am I right in saying that you are breaking both some bosonic symmetry and some supersymmetry?
Not necessarily, in fact. But let me continue. There's both. There's a saddle, both a saddle that breaks. So causal symmetry is always broken, but there is one saddle which breaks it by leaving supersymmetry intact, and there is one which also breaks supersymmetry. And the existence of these two saddles is also very important.
Okay. Mm-hmm.
So, right. So basically, what one then does is one constructs now the effective field theory in a way that is analogous, for example, to the Payan, Lagrangian and the chiral Lagrangian, for example. I guess Weinberg and Lloyd Wheeler and people like that. So we introduce here this field Q. So in the chaos community, by the way, in single particle chaos, this has been introduced by Wegner and Yefetov. And so they like this parametrization in terms of matrices Q, which are related to what we would call the pion field. So tau 3, let's say, is the symmetry breaking vacuum. Okay, then this T generates the full Goldstone manifold, and T we would write it as e to the W in high energy physics, and we would call W the pion field. But so you could rewrite this thing as pretty much literally what you know as the pion effective Lagrangian. And then I want to point out one more ingredient, which is that there is this term here, this leading term here, which is something like a pion mass term. So there is a small explicit breaking of this symmetry. And the small explicit breaking comes from having the energies, all of the energies different. So Z1 different from Z2, different from Z3, different from Z4. This is like a small explicit mass term for the quarks. Okay, so this structure here is completely what you would expect if someone told you write down a pion type model for this pattern of symmetry breaking. Okay, so I showed you here the single particle version. More relevant for us is the many body version, which instead of having the base space to be just space, actually lives on the entire many body Hilbert space. The symmetry principles that go into it are the same. It's just more complicated to write down the terms, and I didn't want to bother you with it. Now, I've sort of shown the RMT average here to motivate the singlet projection. But importantly, for a general quantum system, this is achieved by taking chaotic quantum system. This is achieved by taking the late time limit and perhaps some mild average. For example, in the SYK model, I would qualify this as a mild average, but you might think of even milder averages like an order 1 number of parameters. And again, there are explicit examples known in which this effective field theory emerges explicitly from doing these kind of things. But I want to emphasize that, of course, we're interested precisely in the in the EFT when we cannot necessarily derive it, because that's when it's more powerful than the microscopics. Otherwise, you might as well use the microscopics in the first place. Now, this coset here actually is not random, in the sense that the choice actually is a symmetry classification, and there exists only 10 of these. This is the Cartan classification of symmetric spaces, and it can actually be shown to be the same as the so-called Altland-Zenbauer classification of all of the possible random matrix ensembles. So there is a nice map between these kind of cosets and the usual random matrix classification. So the classification of random matrix systems shows up in this approach as the Cartan classification of symmetric cosets. And in this case, this biosymmetry that I had pointed out earlier, actually becomes literally a Weyl symmetry on the root system. So this is literally the reason for this name. It generalizes to more than four spectral determinants, but we don't need that today. And as I already commented, I mean, it's very important here that we use this graded supersymmetry approach, which to my mind is a somewhat more elegant version of what the replica trick also achieves. But in the replica trick, things get much more complicated. So now, good. So now I've introduced to you this effective field theory. Now I would like to show you how to actually work with it. How do we handle time, by the way? How do I handle time? I have 5 minutes left, I guess.
In principle, yes, but you may go on for 10 more minutes, 10 or 15 more minutes, because you had so many questions.
Yeah. Okay. So now the idea is that.
Sorry, Julian, just one more question. When you say, what would you need many more determinants for higher point functions of rho?
Correct.
Okay, thank you.
If questions are allowed, I would like to ask
yes.
several. First, usually singlets of non-compact groups are non-normalizable. Do you have any problem here like that?
In what sense?
They are not normalizable. Just
no, as states on Hilbert
space.
Space.
But they are not normalizable. That's one. And the second, if you could, is there a flat direction in this potential that you imagine where you break some symmetry? And then what is the role of F and V? What you said, F pi and the pion mass, where do they enter into the physics?
That's good. That's actually the first comment I have here, but so let's postpone that. So the first question is, so no, I don't think that the non-normalizability worries me. I haven't gotten that question. It's interesting, but we're basically doing here quantum mechanics, right? In the end, I'm thinking of a finite dimensional Hilbert space. So H is a 2L by 2L matrix, right? And so I don't think the normalizability issue arises.
Oh, for the bosons, not for the fermions, I'm worried.
But even for the bosons, I mean, they're just, it's just a 2L dimensional vector of bosons.
I'm not sure.
I think it's normalizable. I think it's going to be normalizable. But maybe we can talk about this later.
And the flat potential?
So, I mean, this manifold here is precisely all the directions which have a small mass because of this term here, right? So I don't think, so sorry, or which flat potential actually, sorry.
No,
maybe
you say that you are picking some expectation value. Now it could either be along a compact direction or a non-compact direction. I had a feeling here that you are doing non-compact directions, and then it would be flat to infinity.
But it's hyperbolic space, right? It's two-dimensional hyperbolic space, though, so there's some curvature.
Okay, but you have a symmetry breaking. That means you have to choose one among many.
Yes. Yes. And eventually I will be able to integrate over the entire manifold, and I can get the result by having integrated over the entire manifold. So are you worried that you have to put a cutoff on the non-compact direction?
Maybe or maybe not. I mean,
Well,
in scale invariance, there is a flat direction. When you break scale invariance, that's fine.
So that cutoff will play a role. Maybe I'll point it out when it comes. But I'm not sure that I understand entirely why you say the direction's flat, because it's still just hyperbolic space. So it has a constant curvature space.
You are talking about spontaneous symmetry breaking. It means you have many inequivalent vacua and you choose one, but that means that there are inequivalent vacua, and that's flat.
Mm-hmm.
That's all. Okay, we can go on.
Yeah, okay. So, the third question that Eliezer asked, for this one I have a good answer, which is that he was asking what is this pion constant and so on. So actually this pion constant, decay constant, is basically for us what determines the Taoist time. So now let's actually go to a scale where all of these modes have decayed. Okay, so these terms here do no longer contribute, and the dominant contribution comes from this term. That's of course a choice that we make that has to do with what is the value of f squared. And that means that we have to wait in this context long enough for this to be true. And that defines how long you have to wait, that defines the Taoist time. So now that means, however, that this post-Taoist physics is given by just this term here, which is the term supertrace q z bar. And I fixed the constant that I called v by comparing it to the spectral one-point function. So I can compute the spectral one-point function, and I find that the term here is actually given by essentially 1 over the spectral density. Sorry, equal to the spectral density. 1 over delta is equal to the spectral density. So that's fixed v, and I've dealt with f by waiting long enough. And so that's the definition of the Taoist. So now we need to evaluate this. And we can most easily do this in terms of, well, the pions, let's say. So we had t, which is e to the w, which generates precisely these off-diagonal transformations that were broken. So, however, the key point is that there is more than one of these causal symmetry breaking saddles. So there is one which we call the standard saddle, which is, let's say, at the north pole of this two-sphere. Okay, this is what people call the standard saddle, and this is the one that preserves the supersymmetry. Because it preserves the supersymmetry, it actually has action 0. But then there is one which is at the opposite pole of the two-sphere, the fermionic part, and this is what is called the Andreev-Altshuler saddle, which has an action which is of order e to the minus entropy. So the action of this saddle is not 0, but it's of order e to the minus entropy. And so one comment is that these two saddles are actually linked by the Weil symmetry. So if you know that this saddle is here and you know the Weil symmetry, then you know that the other saddle also has to be there. Okay, so now what we can do is we can just look at the leading contributions to our spectral determinant 4-point function, because that's what we started with. This is what gives us the spectral density. And so the way to do it is you expand it in these pion fields. And so let's start, for example, by the expansion up to quadratic order. This little s here, I apologize, this little s is actually omega over delta. This is just a standard notation. This measures energy differences in terms of the average level spacing. So then the simplest diagram that you get for the 4-point function is basically a contraction between advanced and retarded sectors. Okay, so the spectral determinants themselves, if you expand them in the B fields, you get supertrace BB tilde times projector on fermionic degree of freedom, and a supertrace B tilde B times a projector on fermionic degrees of freedom. This one acts as an advanced projector. This one acts as a retarded projector, for example. And so the simplest contribution is basically just the diagram where you do the simple propagator 1 over s for each of these contractions. And so you get a term, you get a diagram which goes like 1 over s squared. And the fun part of this is that if you take the Fourier transform of this 1 over s squared, you get something that rises linearly in time. This is the linear rise in time.
Sorry, Julian. So if you have two saddles which are connected by a Weil symmetry, then how come one of them is subdominant? I'm missing something very simple, perhaps.
Well, it is subdominant only at the beginning of this ramp, but it actually competes. And when it starts competing is precisely the transition between the ramp and the plateau.
Ah, I see. Okay. So this is not like the wormhole situation in which the wormhole topologies they are subdominant all the time. I mean, I saw also that you wrote e to the power minus s.
Yeah, but you see, this diagram here is non-perturbative. So this is like, so this is 1 over little s, but this is going to be, energy. This is e to the minus 2s suppressed, this diagram, s into being the entropy. So this is like a wormhole contribution.
So
right?
the Weil symmetry is not something which is exact, or
the Weil symmetry really is exact, but I haven't even told you anything about the contribution yet around the second saddle.
Ah, okay, I see.
I hope so. I'll put these together. Okay, so this is the diagram that gives you the ramp, but in order to understand the plateau, you do actually need to understand the second saddle.
All right.
So now, but you can ask what happens for higher order terms. But maybe at this point still, it is important to say that there will be an expansion in 1 over little s squared. But this expansion from the point of view of the original theory is fully non-perturbative, right? This looks like it's a perturbative expansion in 1 over s squared, but each of these little s's comes with powers of e to the big S, right? So this is already something that's down by factors of e to the minus 2 times the full entropy. And so this is a highly non-perturbative contribution if you want to calculate it from the original theory. Okay? Right. And the second saddle will be even further non-perturbatively suppressed. That's the doubly non-perturbative part. Okay, so, right. Now, you could ask what happens to high order contributions, which are basically the perturbative contributions, perturbative in inverted commas, in 1 over little s. And so then you get terms which have higher topology. So for example, this is a non-planar diagram in this expansion. And while it's topologically the same as a genus 1 Riemann surface with 2 boundaries, and it would give you a contribution that goes like 1 over s to the 4th, but actually what the coefficient is depends on the symmetry class. And in particular, in the simplest case, the unitary symmetry class, it's actually 0. But in the orthogonal symmetry class, it can come with a non-trivial finite contribution. Okay. In fact, in the unitary symmetry class, all the higher order corrections vanish, which is actually you can show by using localization. But what I want to point out is that we've only looked at the diagrams around the standard saddle. But the full picture is actually that you ought to take the contributions from the standard saddle, which are 1 over s squared, 1 over s to the 4, and so on. You can have all of these genus G Riemann surfaces with 2 boundaries contributions. But that's not all. In fact, you get the contribution around the second saddle, which is this so-called Andreev-Altshuler saddle, which is a perturbative expansion around the second saddle. Okay. And the Weil symmetry does indeed provide a mapping between these contributions. Okay. I don't know if this was Gautam's question, but so you have an equivalent associated expansion around the second saddle. And so the full theory, you need to actually take into account the sum around both of the saddles. And in fact, if you do this, right, for the GUE, for example, you get the famous sine kernel, which of course Freeman-Dyson calculated using random matrix theory arguments. And so this gives you a 2-level correlation function, which is sine squared s over s squared, which is doubly non-perturbative in the entropy of the system, but its Fourier transform gives you precisely the kind of ramp and plateau structure that we know. So I'll explain that, but there seems to be a question. So please.
Hi, Julian.
Yes, hi.
So far you are yeah. Hi. So so far you are considering at the level of spectral form factor. But let's say if you look at, let's say, 2-point function, and you have this symmetry-breaking pattern which is very universal. So for the 2-point function, you will have some universal answers from this symmetry-breaking pattern. But let's take just only a particular SYK model. Don't disorder average. Then for that particular SYK, look at the and you have some universal properties of that 2-point function. And it might be that the part that is coming from the symmetry-breaking pattern is the part produced by the gravity, in the sense that it does not produce all the details of a single SOK model. It might be exactly the part that is producing the gravity contribution, not not
So
all the details.
I had
You know?
some trouble understanding what you said because of connection, but I think the main gist I got, and I fully agree with it. In fact, this is what I want to say. So the way that I would say it perhaps is the following. I would say that there is a sense in which this rampant plateau, okay, is, you can fish it out of a general theory where you do no averaging. And to fish it out, it's precisely, you say, that it is the contribution of phase coherent processes at late times. Now you can ask, how does the full system behave? Well, it will actually not exactly have this rampant plateau. It will have the rampant plateau plus fluctuations. But precisely what I'm saying, I agree with you, that is that we should think of the gravitational path integral as fishing out only the phase coherent processes. And what I've given you here is a very generic quantum chaotic way of defining, you know, what is being fished out in a generic system. And moreover, what I want to point out is that even a very small amount of averaging. So you have now your envelope function, and then you have, that corresponds to the phase coherent processes. And then you have oscillations on top. But these oscillations can be killed by very small amounts of averaging. So just a small set of parameters. And so that, by the way, is, I think, what is being achieved recently by these CFTs, where people, for example, average over moduli space and so on. But I think there are more questions, so go ahead.
Right. Sorry, should I go ahead and say one more sentence maybe?
Yes.
Hello?
Hello?
Can you hear me?
I can hear you.
Yeah, so you can, you know, so far you are looking at the contribution of the saddle, but what about the fluctuations around the saddle? Because it's a symmetry-breaking pattern, so you know the fluctuations will also be constrained by smaller number of parameters. It's not just some arbitrary fluctuations. So maybe fluctuations around the saddles will give you some amount of into point function, not all of the details of the theory, but just some part of it.
One sec. This is actually one of my points in my conclusions. So let me describe this now, and then I want to maybe just say 2 words about bulk, because it's also interesting to think about this in bulk. Then I'll conclude. Okay, so I need 5 more minutes, I guess, that I was given, and then I'll conclude. So now let me just say the point now is that we can visualize it as following. So this universal ramp plateau structure actually comes from, first, you look only at the standard saddle, small fluctuations around the standard saddle. This is precisely the contributions that are in the JT context, the bulk wormholes of the JT. Okay, I can tell you more about that later. It wasn't very clear from what I said, but it is true. So the ramp is basically these wormholes, and the wormholes can be seen as the universal correlations of phase coherent processes in this effective field theory. However, if you wait longer, so if you look at even longer timescales, at some point you also realize that you need to take into account the second saddle. If you take into account the second saddle, then you find that actually this linear rise gives way to a turnover to the beginning of a plateau. But in order to really understand the plateau at the largest timescales, what you actually need to understand is that now you need to integrate over the entire Goldstone manifold up to a cutoff. Eliezer, by the way, here's a cutoff in the bosonic direction. This is the cutoff, and the cutoff is precisely the inverse of the timescale up to which you want to understand. And what happens is, if you integrate, this is important, over the entire Goldstone manifold, you actually restore the symmetry. There's a symmetry restoration. And why is there a symmetry restoration? Because now there's no longer a cut where the spectral density is non-zero. There is only individual levels, poles. And if you have only poles, then rho is 0 almost everywhere in a technical sense. So the symmetry is restored. So the picture is one of broken symmetry, linear rise. Second, doubly non-perturbative subtle gives you the beginning of the plateau. But to really see the discreteness of the spectrum, you need to integrate over the entire manifold and recover the symmetry, restore the symmetry, and get only individual poles. Now, what I said, so now I really want to say it in words, basically. The terms in this topological expansion are arranged into the same topologies as the expansion of the JT matrix model, which were there interpreted as Euclidean wormholes and baby universes. And in fact, we showed in our paper that this is not a coincidence. I believe you can tell this story also in JT, but we instead told this story in minimal string theory. And we did it in minimal string theory because in some sense, all these results had been worked out by people like Moore and Kutasov and Kazakov and so on. And there are powerful results already available. But surely would be interesting to also, fill in the details in JT here. But the idea is basically, let me just say the idea and then I'll conclude. The idea is that determinants now basically become D-branes. So you can understand this determinant operator as a bulk D-brane, and then you basically need to study the physics of these D-branes. And what happens is that these D-branes, right, also develop spontaneous condensates of open string modes, and these open string modes break the causal symmetry, and this is the story, and we can tell basically the bulk story here. Yeah, I do want to skip that, unfortunately, because it is quite interesting. You can basically associate various bulk objects to all these things that we talked about, okay? Let me just say it like this. And what we find is we go back to the minimal string literature. We basically adapt their calculation to our needs, and we can exactly fit the EFT predictions with exactly the prefactors, with exactly the correct prefactors and so on, okay? And so that means that if we take Liouville as our theory of 2D gravity, then this Liouville annulus is our first contribution. It's the Euclidean wormhole. Then there are corrections which are of higher genus. This is this idea of the creation and annihilation of baby universes and so on. The thing that we do not have a good, let's say, continuum description of is the second saddle. This is the thing that we still don't understand how to do in the bulk, and I think this is an extremely interesting target. What is the second saddle from the bulk perspective? So let me conclude. Actually, you know what? Many of the things have already been anticipated. So there is a bulk picture of causal symmetry breaking in terms of actual branes, not banes, branes. This basically associates this idea of Euclidean wormholes to this topological expansion of our EFT. Here is the comment about erratic fluctuations. How do you deal about, really, so this effective field theory applies in higher dimensions. How do you actually fish out the contributions in the high dimensional bulk? This is this discussion about the, a bulk path integral. Is there a connection to replica wormholes and the page curve? Well, and the last one is basically, I talked mostly about the spectral correlations, but actually you can also talk about operator correlations. And that also should have interesting bulk implications. And I'm just advertising that there is a paper forthcoming with these authors. Thank you, and sorry for going over time.
Okay, so thank you, Julian, for the very nice talk. So maybe we can unmute our microphone and clap up to show our appreciation. Yeah, so this is the time for formal questions, although we had so many questions during the talk. So if you have any question, please unmute your microphone and go on.
Can I ask a question?
Yes, of course.
So there was this Weil symmetry which connected the two saddles, right? So
yes.
What is the bulk interpretation for that?
Sorry, that was difficult to understand. What is the...
Is there a bulk interpretation for the Weil symmetry which you said?
No, but that is definitely the right question to ask. I mean, that's one that we've been thinking about, but I can't tell you what the answer is. But it would be it is tempting to try, because the standard saddle and its perturbative expansion which is, by the way, again, non-perturbative from the point of view of the original theory. But the standard saddle and its fluctuation expansion we understand, and it would be very nice to try and use that to bootstrap your way to the second saddle using this Weil symmetry. And in fact, in some simple chaotic systems, this can actually be done. This goes under the name of the so-called Riemann-Siegel lookalike, and is something that, you know, the sort of more mathematically formal community in quantum chaos has been pursuing, but really only for the simplest models, like random unitaries, stuff like that.
Okay, thank you.
But I think it's the right question to ask. I can't tell you really how it works.
Any more question?
So Julian, is there a natural way in the D-brane picture that the GL2/2 appears?
Yes, I think so. So I would have said that you have basically stacks of D-branes.
Okay.
And if they all coincide, so if all the energies are equal, then of course they have a non-abelian, if you want, world volume symmetry. Sorry, I'm lacking the words here. But at any rate, they have you know, like a non-abelian symmetry. And what we had to do, so I had to basically, by the way, I had to be a little bit faster with the previous results, because what we need is we also need, in some sense, fermionic branes, right? Or rather, what we need is bosonic branes, because you can show that the FZZT branes basically behave like fermionic objects, but we also need the bosonic objects. We need ghost branes. People like to call them ghost branes. And those ghost branes naturally have, when they're all coincident, SUN/M symmetry.
Yes.
And in fact, I didn't talk much about this, but this GLN/M symmetry, once the dust settles and you really regulate all the integrals of the Goldstone manifold, it actually becomes an SUN/M symmetry. So this is how you can see that symmetry from the point of view of the branes.
I see.
But we had to cheat a little bit by basically claiming that we understand ghost branes. And actually, in a technical sense, it would be very interesting to make that precise. What you could do, of course, is you could instead use replicas, in which case you only have standard FZZT branes that are well understood. The problem is that then the effective field theory formulation becomes much more cumbersome. So there's some kind of you know, conservation of pain.
Right. Okay, thank you.
Any other questions?
Hello.
Yes.
For me. So, so this is regarding your comment that you can have like more determinants for higher point functions and so on. Do you have a rough idea whether there's a similar symmetry breaking patterns for those lengths for higher point functions of rho phi?
Actually, yes, I have slightly more than a rough idea, because there is a paper by Zernbauer which actually makes such a claim.
Mm-hmm.
It's, yeah.
So what is the statement? If it is,
there is basically another classification. So, you know, Zernbauer was very interested in these co-sets, and there is another classification, but I think, if I remember correctly, it's just sort of like products of what is already known. So you don't get some new symmetry class, but you sort of combine what you have to make bigger objects.
and this is for any endpoint function, any k point function. This is true.
That's the claim.
Okay. So roughly when is this Zernbauer's paper? Do you know? Just to
Sorry, where?
roughly from when is it?
This I don't know, but I can send it to you if you want.
Okay, yeah, that would be great. Thank you.
Any other questions?
Yeah, I haven't been able to say one particular thing. There is also like a nice role here for this Koncevich matrix model, cubic matrix model that comes out. except that we need some sort of super Kontsevich cubic matrix model because we have, again, we have these ghost brains. So I don't know if this object is well studied, but as I said, just sort of following our nose, we just used it. But it's actually very nice that this Kontsevich matrix model somehow reappears also in this context.
Like, can I understand this claim about this minimal string theory and so on and so forth as a statement that many different systems have some, at late times, have some effective minimal string theory or something like that?
Well, I haven't thought about it that way. Actually, let me just tell you the way that I thought about it is that we take a particular model that has sort of like a bulk, I mean, an open-closed duality, and we describe the chaos effective field theory from both points of view. And what happens is that this minimal string theory itself already contains more than just the effective field theory description. But what we can do is we can show that the same dominant contributions at late times arise there as in the chaos effective field theory. So already we basically only look at the leading singular contributions to various diagrams. So I was just thinking of minimal string theory as an example again of a system that shows complex behavior, but that reduces to the universal predictions at late times. Now, JT gravity is another such system. But I think it's what you say in general is an interesting point, which is how do I deal with the fact that this chaos effective field theory from the field theory point of view indeed gives these kind of, let me call it minimal string theory-like contributions for a general field theory. And to me, somehow there should be a subsector of these theories, even of the bulk at late times, in which you can actually identify topology, right? Because there is definitely no genus expansion in higher dimensional gravity. Sorry? Sorry, yeah, crosstalk. So, however, there might be some kind of subsector, okay, which is effectively classified by these diagrams. And so this subsector, as you were just suggesting, I mean, it is in some sense related to minimal strings or 2D JT, I mean, two-dimensional models of gravity.
Okay, thanks.
Any other question to Julian? It seems that there are no more questions. So thank you, Julian, again for the nice talk. So I know that you are tired. You already gave like 2 lectures in the morning and you are talking here. So thank you very much for this very nice presentation. So thank you everyone for joining us today. So I wish everyone to have a very nice time. So have a nice day, Julian.
Thank you, and you all too, and see you hopefully in person sometime soon. Bye-bye.
Sure. Bye-bye.
Thank you. Thanks, Julian. Bye.